So just to present Manuel, he completed a bachelor's degree in metallurgical and materials engineering at Instituto Superior Técnico in Lisbon, followed in '93 by a PhD in fracture mechanics of high-speed steels at University of Bradford at the United Kingdom. His main research fields have been the powder metallurgy of high-speed steels and heavy alloys, the mechanical behavior of metallic alloys at high temperatures under creep and fatigue conditions, and more recently, the mechanical behavior of light alloys and composite materials. In addition to his research work, he has been invited lecturer at universities and higher education institutes in Portugal and has served as head of the mechanical testing laboratory at ISQ for over 20 years. So, welcome. Here.
Thank you very much. Good morning, everybody. I am here and with this presentation talking a little bit about mechanical testing, particularly of composite materials, and a bit focused on fiber reinforced composites, which are the most challenging ones to have to test and to determine mechanical properties of those materials because of higher heterogeneity of those properties and higher anisotropy of those properties. So my presentation is a bit biased towards that. Some of the concepts and the tests that I'm talking here, and this is a very brief talk about the mechanical properties, are more focused on that type of composites, but they are obviously applicable to many others and almost all other types of composite materials. So composites combine two or more phases to develop or to enhance some properties of materials, usually developed because of their light weight or their reduction of weight compared with traditional metal alloys, but that reduction and that combination of two different materials, it's also their major problem. It's their major advantage and their major problem from the testing point of view. And I am a man from laboratories, as the introduction said. I always been connected with testing of materials. So this lightweight reduction obviously doesn't, it's not strange that they started usually or at the beginning many decades ago in the aerospace and automotive industry, exactly because of the driving force to reduce weight to improve fuel efficiency and performance. And more recently, because of environmental concerns, which are every year more accurate. So the mechanical characterization is fundamental for designing purposes and also for safety and performance validation of our materials for their practical application in practice. So composites are very much used in very demanding industries like wind energy, aerospace, and automotive, which represent probably more than 50% of the use of composites. By the way, I am a bit focused also in polymeric-based composites. There are other forms of composites, but when I mention composites, I'm referring to these polymeric materials. So, as I said, one of the major problems on these characterizations are the anisotropy or the potential anisotropy of properties compared with metal alloys, traditional metal alloys, which are mostly isotropic. So usually we can do some limited number of tests and they are valid for the bulk of our material. With composites that might not be true. It could be true in some composites with short fibers or particles, reinforced with short particles or fibers, but not with longer fibers and fiber orientation. And in there, we can have a very large variety of properties, as you can see Oh, there. No, it's here. Okay. As you can see there, where we have represented the variation of tensile strength of the material regarding to the fiber orientation of that composite. They might have also other problems like, besides this heterogeneity, like scale effects. So differences between microstructural behavior and macrostructural behavior resulting from the interaction between the matrix and the fibers. They are also usually one of the advantages of composites or polymeric-based composites is their reduced sensitivity to corrosion, but they are not immune to the environment, and they can be sensitive to moisture absorption, for instance, which can reduce their properties significantly or somehow. You see in this figure here, the reduction of mainly ductility resulting in a composite, a polymeric-based composite, biodegradable, so similar to what is being done in REDONDO, and due to moisture absorption. So the polymer was exposed to a moisturizing media, basically water, to absorb that water for several weeks, and we can notice indeed some reduction of their properties. Not much actually for what was expected in this work. Obviously, some of these can be, especially the anisotropy, can be a bit overcome by using layered material in which we orient fibers in different directions to eventually reduce or avoid a bit of the anisotropy effects. This anisotropy or orthotropic behavior in different directions means that to characterize a composite, we need to test in different directions, typically at 0 degrees, 90 degrees to the fibers, and eventually 45 degrees in order to get a better characterization of their mechanical properties. Obviously, the anisotropy or the potential anisotropy also affects, for instance, properties like the load transfer between fibers and the matrix, which in turn affects the crack propagation or defect propagation and potential failure modes, as is depicted here at the bottom, in which we can have failures of the fibers themselves together with the matrix, or in other directions other than the longitudinal direction, the 0 degrees direction, we might shift into cohesive failures in the matrix itself or adhesive failures between fibers and that matrix. Fibers or other reinforcement media that is used. So typically there are not really many specific tests for mechanical characterization of composites or polymers. They are mainly the same ones that are used in type that are used before for metals, with some adaptations for the material itself. So basic mechanical properties usually are evaluated by tensile, compression, or flexural stress in 3-point bending, compression, or just tensile. Typically, we need for compression some special devices, special jigs to prevent buckling of the specimens, which are usually also instrumented with strain gauges in their gauge length to monitor eventual buckling of that specimen and sort of artificial reduction of the properties that would affect our evaluation of the composite. Not so often, but also I call them advanced mechanical properties. Here might be an abuse of language because they are not really very special tests, but are tests that go a bit further on the characterization of the mechanical properties because they deal with some intrinsic properties that are a bit more difficult to understand and to measure in a composite or in other materials. And they are usually related with impact resistance. Impact in the metals is a bit more easy than here, and we will know, we'll present why in a little while. But then to determine other things that are very important for some more demanding applications of our composites, which are the interlaminar strength and eventually the fracture toughness of that material. Fracture toughness is always determined for metal alloys before, although here the techniques are a bit different, but they, like in more conventional materials, when we talk about fracture toughness, we are usually talking about defects as well. So what I depicted here is a procedure for polymers and especially composites that was developed. It's not a standard method, developed at INEGI in Portugal. INEGI, it's an institute associated with the Faculty of Engineering of Porto University, and involves the testing of 6 different specimens, which are normally called double-edge notch beam specimens because they have 2 notches in opposite edges there, and to test 6 different specimens, increasing dimensions, both in tensile and in compression, to determine what is called usually the resistance curve of that material. So which is a measure of their fracture toughness. The interlaminar strength, it's another property that is quite important for laminated composites, and involves the determination of the strength of the adhesion between layers, different layers of fibers that are used for those composites. And that usually involves the introduction of a defect, usually by inserting a Teflon or other material, similar material, between 2 layers of the material at mid thickness, and then try to open that pre-existing defect to measure their propagation and study their propagation across the material. So usually can be done in so-called mode 1 opening, which is depicted there, which is usually by tensile, can be done by flexural, which introduces the so-called mode 2, which is shear, and eventually a mixed mode between 2 of these modes, which require some special rigs. Okay. Not really connected with the mechanical testing itself, but more with the monitoring of those tests and the data acquisition of those tests are some important techniques that are that have been developed in recent years or decades, or that they have been under development, like, for instance, digital image correlation and acoustic emission. These were already used before for metal alloys, but they are particularly interesting in the case of composites, whatever their nature. For instance, acoustic emission can be used to detect and identify failure initiation in materials. Unfortunately, I did not have the application of the method for a laboratory specimen like we are talking here. So this is a sort of a small component that we tested some time ago for some work, and in which we have an array of acoustic emission sensors there. By knowing those locations of those sensors and the distances between them, we can have them, with some analysis software, identify precisely when fracture starts, so when the material starts to break and producing some characteristic noises that can be identified, and the physical location of that initiation, where it started physically. Digital image correlation is also something that is not entirely new. It's been around for some years, but it's particularly useful in the composites, because in digital, with digital image correlation, we can have 2D or even 3D images of our test specimen or test component, and we can have a full field strain mapping, a mapping like infinite elements analysis, where we produce those stress, strain, whatever distribution maps for our all component or specimen of interest. But then, besides the overall behavior of our component or specimen, we can then analyze in more detail some particular areas of interest, like stress concentrations or defects or whatever. Another techniques that have been very interesting for this testing are, for instance, which are not so much applied to the test itself, but for the analysis of the test results, are the thermography, ultrasonic, and computerized tomography. These techniques, probably thermography can be used as well, theoretically, for the test itself, to monitor the test. Here we have the evolution of a defect in a specimen during a fatigue test, and the evolution of that test that was identified by thermography. It must be used with some care, because particularly in composites, because it involves temperatures and elevated temperatures, well, between inverted commas, but could affect the material, because composites are not very famous for their heat resistance. Ultrasonics are also not a brand new technique, but in modern times, with the development of softwares and other analytical tools, we can access the interior of our material. So what we have here on the right-hand side is a panel that was tested in impacts, as we mentioned before. Before test, and at the bottom after test. You see that there is no visible damage on the surface of our specimen due to that impact, but an analysis with C-scan, ultrasonic C-scan, reveals that almost 1/3, or something like 1/3 of our specimen was completely damaged by the lamination, interlayer delamination on the inside, and that is not entirely visible just with a visual observation. The same goes into tomography, which is a very powerful tool to identify internal defects in our materials and localize them. The image here is a tomographic image of a section in the middle of one of these test panels, in which we can see a localized defect there in the middle. Specifically, this panel was to produce those specimens for mode 1, mode 2 testing for the interlaminar testing, resistance testing, in which it was difficult to identify the location of that initial defect, and tomography can allow this very, very well. So just to conclude, the mechanical characterization is quite complex, although fundamental in composites, because of that dual nature of those composites. And concerning the mechanical testing, is probably fundamental in the coming years, the development of multi-axial testing, usually to address better that anisotropy, finite element modeling as well, to better understand the behavior of those composites, usually also a more standardization of layup and test protocols in order to be more comparable and better quality of analysis, and probably together with the FEM modeling, also the use of machine learning, digital twinning, and other tools that are developed right now in order to probably evolve into what we call virtual testing rather than physical testing, which will open and broaden the application of these tests to more materials and future materials. Thank you very much.
Thank you.